I want you to imagine like the perfect supply chain. Just really picture the mechanics of it in your mind.
Oh, it's a nice thought.
Right. It's like this beautifully choreographed ballet. Materials arrive at the loading dock at the exact moment they're needed.
Yep.
Machines process them in perfect sequence. The finished products slide off the assembly line right into waiting trucks, and they arrive at the customer's door perfectly on time.
Flawless execution.
Exactly. There's no wasted space, zero friction, no capital tied up in excess inventory, just a masterpiece of modern engineering.
It is a beautiful image. And, well, unfortunately, anyone who has spent more than 5 minutes on a factory floor or, in a logistics hub knows it is entirely a fantasy.
Completely. Because reality is just chaos.
Absolute chaos.
Reality is like a massive container ship getting stuck sideways in a vital canal.
Right.
Or it's a sudden viral trend that causes demand for a specific component to just triple overnight.
Yeah, or a supplier sending you a pallet of raw materials and half of them fail quality inspection.
Exactly. The illusion of perfection just shatters the second a rigid plan meets an unpredictable world.
And that collision, that tension between a theoretical plan and a chaotic reality is the core focus of our deep dive today.
Yes, Sid.
We are exploring the mechanics of Module 4, Section H, which really zeroes in on how companies actually respond to supply disruptions and demand changes.
So we're going to unpack how material requirements planning systems, or MRP systems, actually adjust to these shockwaves.
Because they have to.
Right. We'll look at the highly complex math used to minimize costs, the hidden psychological traps of playing it safe with buffers, and the cutting-edge predictive technology that's just fundamentally changing how we look at the future.
Yeah, because dealing with these disruptions isn't just about, a planner frantically making phone calls to expedite a late shipment.
Though I'm sure there's a lot of that.
Oh, plenty of that. But it's really about how the entire MRP ecosystem is calibrated mathematically to absorb variables without collapsing into complete system failure.
Right. So, to understand how to fortify that system, we first need to look at how reality breaks it.
Good place to start.
When we dive into the concepts in Module 4, the core ways variability hits an MRP system form this specific matrix. We're looking at 4 main culprits, what I like to think of as the 4 horsemen of MRP variability.
I like that. So you have demand versus supply on one axis, right?
Right.
And on the other axis, you have quantity versus timing.
Right.
So a shift in any one of those 4 quadrants creates an immediate ripple effect.
Let me put this into a scenario to kind of ground it for you. Let's step away from the factory floor and imagine you run like a high-end catering business.
Okay, catering.
Yeah, and you are executing a 500-person corporate gala. You have your master production schedule completely locked in.
So every ingredient, every prep station, every serving time is mapped out.
Exactly mapped out. So the first horseman is demand, quantity, variability.
Right.
In the catering scenario, this is the client walking in 2 hours before the event and saying, hey, we just had 50 VIPs fly in. We need to add a few tables.
Ah, a classic panic moment.
Right. Your customer suddenly needs 550 units instead of 500.
And that immediate shift upward just invalidates your baseline assumptions. But, it can also swing the other way. Demand could drop abruptly, leaving you with all this excess perishable inventory.
Right, which is just as bad. Then we have demand timing variability.
Okay, so a shift in when they want it.
Exactly. This is when the client decides to cut the opening speeches short and they want the main courses served 45 minutes earlier than contracted. So the demand moved earlier by a specific number of periods.
So that's the demand side. Flipping to the other side of the matrix, we hit supply quantity variability.
Right. So this is when your seafood vendor delivers the sea base, but when your sous chef inspects it, like 20 pounds of it is spoiled.
Ouch.
Yeah. Or it could be internal scrap. Your line cooks accidentally burned 3 trays of appetizers.
It's also ouch. So either way, the supply of usable material is lower than the required quantity.
Exactly. Which brings us to the final variable, supply timing. You ordered specialty linens from an external vendor, but their truck is stuck in a massive traffic jam.
So the supply is delayed past the point of necessity.
Yep. And honestly, when you lay it out like that, it's kind of a miracle anything gets built or delivered at all.
It really is.
So how does a software system actually process one of those hits? Say the seafood vendor shorts you 20 pounds of fish. How does the MRP grid react?
Well, the system operates on strict interconnected logic. The primary heartbeat here is the projected available balance.
Okay, the projected available balance.
Right. That's a rolling calculation where the system takes your current on-hand inventory, adds any scheduled receipts coming in, and then subtracts your gross requirements.
And the gross requirements are the actual materials needed to fulfill the master schedule, right?
Exactly.
So it's literally the system checking the digital walk-in fridge, adding what the delivery truck is bringing this afternoon, and subtracting what the cooks actually need to put on the plates tonight.
Precisely. So if a vendor shorts you, or you have a massive scrap event, your projected available balance suddenly drops below zero for a future period.
Uh-oh.
Yeah, so the system immediately recognizes a net requirement. It calculates that it will run out of materials, so it generates a planned order release to compensate.
And it offsets that order by the established lead time.
Exactly.
But wait, if the lead time for specialty C-Base is 3 days and the gala is tonight, the math breaks down.
It does. The system basically generates an exception message, effectively throwing its hands up.
Wow.
And because MRP is hierarchical, a single delayed delivery or shorted quantity just cascades down the entire bill of materials. It forces recalculations for every single subcomponent beneath it.
Just completely rewriting the schedule.
Yep.
So knowing that these 4 variables, timing and quantity on both the supply and demand side, are constantly threatening to rewrite the schedule, how do supply chain professionals actually fight back?
Well, the primary line of defense seems to be manipulating lot sizing parameters.
Essentially, changing the mathematical logic of how much they order at any given time.
Right. Because every time a company places an order, they are trying to balance a very delicate seesaw between 2 competing financial forces.
Okay, what are they?
On one side, you have ordering costs. Every purchase order requires administrative labor, transportation fees, receiving, inspection.
Which naturally makes you want to order as infrequently as possible to minimize those transactional hits.
Exactly. But that pushes down the other side of the seesaw carrying costs.
Ah.
If you buy a massive bulk order just to save on shipping, you now have capital locked up in inventory sitting on a warehouse shelf.
Right, you're paying for insurance, security.
And the opportunity cost of that frozen cash. So the ultimate goal of lot sizing is to find the mathematical sweet spot that minimizes the sum of both the ordering costs and the carrying costs.
Makes sense. Now, there is a simplistic approach mentioned in the sources called lot-for-lot ordering, where you just order the exact quantity you need for that specific period. Like, need 12 units for next week, order 12 units. But that method completely falls apart when demand is highly variable, right?
Oh, yeah. Lot for lot is catastrophic for your margins when you have low sporadic demand.
Why is that?
Well, if a manufacturer only needs 3 specialized microchips next Tuesday, and then maybe 2 the following Friday, placing individual orders means they're paying high setup and transportation costs for these tiny quantities.
Oh, I see. The transactional fees rapidly outpace the actual value of the materials.
Exactly.
Huh.
So to fix that, they bring in models like economic order quantity, or EOQ, and period order quantity, POQ.
Right. EOQ and POQ.
EOQ is fantastic when demand is relatively steady and predictable. It calculates a fixed static quantity that minimizes total costs.
Okay.
And POQ places orders that cover a fixed number of periods. But again, when those 4 horsemen of variability are running wild, a static model breaks.
You have to move to dynamic methods. And this is the part of the methodology that absolutely fascinated me. The dynamic models, things like least total cost, part period balancing, the Wagner-Whiten algorithm, and the Silvermeal heuristic.
Very impressive names.
Right. These aren't just rules of thumb. These are advanced mathematical formulas calculating the exact tipping point of that seesaw in real time.
The Silvermeal heuristic is a perfect example of this in action. Its objective is to find the least period cost.
Okay, break that down for me.
Let's say a planner is looking at an MRP screen, and they have highly erratic demand projected over the next 6 weeks.
Spiking one week, dropping the next?
Right. The Silvermeal algorithm starts by looking at just week 1. It calculates the setup cost to place that single order.
Okay.
Then it asks a mathematical question. What if we combine the requirement for week 1 and week 2 into a single order right now?
So you save an entire setup cost for the second week.
Yes, but now you have to pay carrying costs to hold week 2's inventory for an extra period.
Ah, the seesaw tips.
Exactly. The algorithm adds the single setup cost and the new carrying cost together and divides by 2 to get the average cost per period.
And because the hefty setup cost is now divided across 2 periods, the average cost per period likely drops, making it mathematically smarter to group them.
That is the core mechanism. Silvermeal then simulates adding week 3's demand into that same batch.
It just keeps rolling forward.
Yep. It calculates the carrying costs of holding week 3's inventory for 2 extra periods, adds it to the total, and divides by 3. It keeps rolling forward, period by period, constantly checking that average cost per period.
Until the carrying costs finally catch up.
Exactly. The exact moment the math tips. When the cumulative cost of holding all that future inventory outweighs the savings of avoiding another setup fee, the average period cost starts to go up.
Oh, wow.
The second that average cost ticks upward, the algorithm stops. It draws a line and says, this is your optimal lot size for this specific order.
That is incredibly elegant. For every single order.
It is.
But this brings up a huge operational friction point.
Always does.
Right. If the Wagner-Whiten algorithm or the Silvermeal heuristic are mathematically superior, if they dynamically optimize total cost to the penny, why is there so much resistance to using them?
Good question.
The literature points out a massive caveat. If the human users don't understand the logic, they literally won't use it. Why not just automate it and lock the humans out?
Because supply chain execution is fundamentally a human endeavor, and it's heavily driven by risk aversion.
Risk aversion.
Planners are the ones who get fired if the assembly line stops because they ran out of parts.
Sure.
Imagine a veteran planner looking at their MRP dashboard. They know their average historical demand for a component is about 500 units a week.
All right.
Suddenly, this black box dynamic algorithm tells them to order 4,500 units today and nothing for the next 2 months.
Every instinct they have is going to scream that the system has a glitch.
They will assume the software is broken. If they don't understand why the system is suggesting that massive lot size, perhaps the algorithm is getting ahead of a projected capacity bottleneck or grouping orders to offset a predicted spike in carrying costs, they will manually override the system.
Oh, no. So they just delete the recommendation.
They will delete the 4,500 unit recommendation, punch in their comfortable 500 units, and instantly defeat millions of dollars of algorithmic optimization.
Oh, wow. The ultimate tension between mathematical efficiency and human psychology.
Absolutely.
So if planners fundamentally distrust these black box algorithms to handle the chaos, how do they protect themselves? It seems like they bypass the math entirely and just build physical walls.
Yes, they utilize buffers. When algorithmic optimization feels too risky or opaque, planners rely on padding the system.
Padding the system.
The 3 primary mechanisms for this are safety lead time, safety stock, and yield factors. Okay, let's break those down for everyone. Safety lead time protects against timing uncertainty.
Exactly. So if a supplier contract guarantees delivery in 2 weeks, the planner sets the MRP parameter to 3 weeks.
Yep. And then safety stock protects against quantity uncertainty.
Right.
You mathematically only need 1,000 units to meet the schedule, but you mandate that 200 extra units must always sit on the warehouse shelf, completely untouchable under normal conditions.
Just in case. And finally, yield factors. Those adjust the starting quantity to account for expected scrap.
Exactly. If a specific machining process historically ruins, say, 5% of the raw materials, the system is programmed to automatically inflate the starting materials by that percentage, so the net output meets the requirement.
The operational benefit here is totally clear. Buffers act as shock absorbers for the minor day-to-day variability.
Right.
If a truck gets a flat tire and is a day late, the safety lead time catches it. The factory doesn't even notice. And this directly prevents a phenomenon known as MRP system nervousness.
Oh, system nervousness is a crippling issue in lean supply chains.
How so?
Without buffers, an MRP system is incredibly hypersensitive. If an inbound shipment is delayed by just 4 hours, the system might react by generating hundreds of frantic exception messages.
Just panicking.
Yes. It tells the planner to reschedule sub-assemblies, expedite freight, cancel adjacent orders. It creates a chaotic noise floor of false alarms.
And buffers quiet that noise by absorbing the minor tremors before they trigger an earthquake.
Precisely.
But there is a massive inherent catch to this strategy.
There always is.
By implementing buffers, you are fundamentally corrupting the integrity of your own data. You are intentionally feeding false inputs into the MRP system.
You are instructing the software to lie to itself to protect the schedule.
Yes. And I was trying to conceptualize why this is so dangerous long-term, and I realized it's a trap we all fall into in our personal lives.
Oh, yeah.
It is the exact same psychology as setting your bedroom clock 15 minutes fast so you aren't late for work.
Oh, that's an excellent parallel for system corruption.
Right. It works brilliantly for the first week. You wake up, look at the clock, panic, and you rush out the door. That 15 minutes is your personal safety lead time.
Absorbing all the minor morning disruptions.
Exactly. Spilling your coffee or having to scrape ice off your windshield, you get to work perfectly on time, but eventually your brain figures out the trick.
You start doing the mental translation.
You do. You look at the clock, you see 7:15, and your brain immediately subtracts the buffer. Well, it's actually 7 o'clock. I have time to make a second cup of coffee.
Yep.
You start ignoring the tool that was designed to create urgency in the first place. And that creates a brand new kind of system nervousness because now you are constantly second-guessing your own baseline data.
That psychological degradation happens on a massive scale on factory floors.
Really?
Oh, absolutely. If a production team knows that the system's lead time is artificially padded by 2 weeks, they start ignoring the system's urgency. An exception message pops up on the planner's screen saying, critical, release order now. And the planner thinks, that's not actually critical. That has 14 days of safety lead time baked into it. I'll process it next Tuesday.
So they stop trusting the system entirely because they know the system is crying wolf.
Exactly. This is why supply chain leaders are warned that you cannot just set a buffer and walk away.
It takes maintenance.
Intense maintenance. Buffers require constant monitoring of throughput speed and abnormality status. System users need rigid operational definitions.
Like, when are they legally allowed to eat into the safety stock?
Right. Is this exception message a genuine line-down emergency? Or is it just the buffer being consumed? If the entire organization isn't completely aligned on how to interpret the lies they told the system, the master schedule just devolves into chaos.
So if complex dynamic math is often overridden by nervous humans and building buffers forces us to lie to our own systems, what is the evolution of this? How do we actually build a resilient supply chain?
Well, the answer seems to be moving away from reacting to chaos and instead simulating the future before it happens.
Okay, so we are transitioning from rigid MRP grids that look backward into dynamic ecosystems that use advanced feasibility checks and validation models to look forward.
Precisely. And the methodology makes a stark distinction between two predictive tools here: what-if analysis and full simulations.
Break this down for me.
A what-if analysis is typically a single variable stress test.
Single variable.
Right. A planner might isolate one factor, say, what happens to our projected available balance if our primary steel supplier increases their lead time from 4 weeks to 8 weeks?
Okay.
The system recalculates that single thread, and the planner can see the isolated impact.
So it's a targeted hypothetical.
But a true simulation is exponentially more robust. It is a multivariable stress test over a defined range.
Oh, wow.
A simulation tests the MRP plan by simultaneously fluctuating demand by 15%, increasing expected scrap rates by 5%, and injecting random shipping delays across multiple supply nodes.
Testing all the horsemen at once.
Exactly. It stress tests the entire architecture to see where the capacity and material constraints actually break.
And this is where we cross the threshold into modern tech. We are integrating these simulations with AI analytics and the IoT, the Internet of Things.
Yes.
This allows systems to continuously replan based on real-time data, enabling predictive maintenance and dynamic parameter adjustments.
It replaces the manual spreadsheet calculations with thousands of simultaneous Monte Carlo-style probability matrices.
It's mind-blowing. I want to visualize this difference for you. Compare the old reactive MRP methodology to an AI-driven, IoT-connected supply chain handling a major disruption.
Okay, let's look at a critical piece of machinery on an assembly line.
Okay.
In a legacy system, a vital bearing inside that machine begins to degrade. Nobody knows. 10 days later, the bearing shatters.
The machine seizes and production immediately halts.
Yep. You now have a catastrophic supply quantity and timing failure. The planner receives a frantic call from the floor, logs into the MRP system, and realizes they are going to miss their master schedule for a massive client.
And the only solution is brute force.
Total brute force. They have to manually expedite replacement parts via air freight at a 400% markup, schedule emergency weekend overtime for the maintenance crew, and heavily consume their safety stock just to keep a trickle of finished goods moving.
Pure reactive panic.
Now run that exact same degrading bearing through the modern AI-integrated ecosystem.
Let's hear it.
The bearing begins to degrade. But this time, it has an integrated IoT vibration sensor.
Oh, nice.
The sensor detects a microscopic anomaly in the acoustic signature of the machine. It feeds that telemetry directly into the AI analytics engine.
Okay.
The AI cross-references historical failure rates and determines that this specific vibration pattern means the bearing will experience a catastrophic failure in exactly 12 days.
So it knows the future before the machine even shows physical signs of wear.
Exactly. And the AI immediately triggers a multivariable simulation in the background. It analyzes the master production schedule and calculates that taking the machine offline for 4 hours next Tuesday for predictive maintenance is the least disruptive window.
Unbelievable.
And it automatically generates a work order for the maintenance crew.
But wait, what about the materials flowing into that machine? If it's down for 4 hours, doesn't that cause a pileup of raw inventory?
That is where the dynamic lot sizing integration happens.
Oh, of course.
The AI automatically adjusts the economic order quantity parameters for the raw materials scheduled to arrive next week. It dynamically slows down the inbound supply chain, delaying specific shipments by a few hours to prevent a bottleneck on the floor.
Perfectly balancing the carrying costs against the temporary capacity drop.
Exactly. It orchestrates the maintenance, adjusts the inbound flow, and protects the outbound customer delivery date.
All without a single human planner having to set an alarm clock 15 minutes fast.
Right. It replaces the blunt instrument of a static buffer with surgical, real-time precision. The system doesn't need to lie to itself with artificial safety lead times because it possesses actual predictive foresight.
It is truly staggering to think about how these methodologies have evolved.
It really is.
I mean, we've journeyed from understanding how the four horsemen of variability, those unpredictable shifts in supply and demand, can shatter a rigid master schedule.
Yeah.
We've unpacked the incredibly elegant math behind dynamic lot sizing, finding that exact tipping point between setup costs and holding costs.
And we examined the very real psychological friction of supply chain management, seeing how human risk aversion leads to the implementation of buffers.
Right, and how those false inputs can slowly degrade the trust in the entire system.
And finally, we looked at the horizon, where AI and multivariable simulations are stripping away the need for those psychological crutches.
Predicting the chaos and dynamically rerouting the supply chain before the disruption even occurs.
It represents a fundamental shift in how we build global logistics.
It does. And it leads me to a lingering thought that I want to leave you with.
Okay, let's hear it.
If AI analytics and predictive simulations become so flawless that we can entirely eliminate safety stock and safety lead times, we achieve ultimate efficiency. We achieve that frictionless ballet of zero waste that we imagined at the very beginning of this deep dive.
The dream.
The dream. But it begs a serious question. If we strip every single buffer, every physical safety net, and every extra piece of inventory out of the global supply chain, relying entirely on the continuous perfection of a predictive algorithm, does that make our world incredibly efficient or terrifyingly fragile the moment the power goes out?
A perfectly lean system has absolutely nothing left to absorb the shock of the truly unimaginable.
Something to chew on the next time you order a package and it magically arrives at your front door the very next morning. Thanks for joining us, and we'll catch you on the next deep dive.